Often we can't neglect the effect of air resistance. We've been living in a dream world up till now where we're saying, air, who needs it? But obviously that's not realistic. Drag is a resistive force for anything moving through a fluid, and a fluid can be liquid or gas. And the magnitude of it depends on the viscosity of your fluid. It depends on the speed through which you're going through it. And it will also depend on the cross-sectional area, if it's a large shape versus a small shape, but also the aerodynamic properties of it. That's why F1 cars are shaped that way for their aerodynamic properties. Obviously, there's other stuff going on. They're trying to redirect the air upwards so that by Newton's third law, if as the car progresses forwards, the air goes upwards, that means the car is forced down, so it can get more friction and stay on the road, and it's all very exciting, I'm sure. For any F1 fans out there, plenty of physics at play. Right, coming back down to Earth again. As an object accelerates under a driving force, its velocity increases. Therefore, the drag force on the object also increases. Yep, that stands to reason. I believe in your formula sheets, you will nearly always have, there's an equation for drag, which sometimes comes up in exams, but it's not normally one of the more popular topics. Eventually, the drag force balances the driving force. The object is now in equilibrium. Nice. Okay, so yeah, this is a sort of chronology, a short history of fast objects. If you are stationary, there's no cause for friction with the air. There's no cause for air drag. As you start moving, well, if you're at a low velocity, there's still not going to be that much drag. The amount of air you're displacing per second is not a huge amount. And yes, air has some mass, but it's not as massive as if you were, moving into a wall or a person or whatever, or a vat of honey or something else that's far more viscous and tricky to move. But the faster you go, the larger a volume of air you're moving and having to displace per second. After a while, that does stack up. According to Newton's first law, the object stops accelerating. Okay, so yeah, eventually you will reach a velocity such that you've got your driving force, accelerated down to the max. At first, there'll be no drag when you're at low velocity. And then as you speed up a little bit, there'll be some drag. And then the final phase of this little story, the drag will have increased until it matches your driving force, at which point there's no resultant force, and therefore F equals ma. If there's no resultant force, there's no acceleration. And so you've reached your max velocity. You can't go any faster. It is literally your terminal velocity. An object at rest or moving at constant velocity will remain so unless acted upon a resultant force. There's no more resultant force. Therefore, you are traveling at constant velocity. Sad times for anyone who wants to, go faster and faster and faster forever. Okay, let's look at an exam question. A parachutist jumps from an airplane. This is as soon as you see that, you should probably be thinking, it's terminal velocity. After they've reached terminal velocity, the parachutist pulls their parachute. Describe and explain, again, that famous double act of command words. Describe and explain with reference to the forces acting on the parachutist, the motion of the parachutist falling under gravity. So tell me what you will see. Let's describe, will the velocity decrease? Will the acceleration decrease? La-di-da-di-da. And then explain. Tell me about drag. Tell me about how the forces are changing. Tell me, tell me how the acceleration is changing. The motion of the parachute is falling under gravity before and after they deploy their parachute. 5 juicy marks. Okay, remember, keep it to bullet points. I don't necessarily need the life and times of a parachutist. Each point should reference a change in motion. Yeah, I think that's reasonable. if you're asked to narrate the chronology of this, just sort of do it in chronological order. Keeps it nice and simple. Include both for full marks. I assume it's referring to describe and explain. Okie dokie. So, immediately after this fella has been dumped out of his plane, and it looks like he's a little bit surprised. Right, you're falling out of a plane. The parachute has yet to be deployed. You'll accelerate under gravity. Point number one. Might seem easy, but yeah, you get a mark for just saying that you fall. Basically, you accelerate under gravity. As the parachutist accelerates, so its velocity increases, the magnitude of the drag force opposing this motion, or their weight, or their acceleration, whatever, increases. I've written the drag is proportional to v squared. I referred earlier to an equation in your formula sheets, your formula books. I believe that is the one they give you. Ultimately, aerodynamics is quite a complex topic, and it's not particularly well understood even by professionals. But when you're going at sufficiently high speeds, it's roughly proportionate to v squared. But that's not an essential part of the answer. If that bracketed bit wasn't there, they'd be scoring that mark anyway. The acceleration decreases until the drag force is balanced by their weight. Yeah, that's true. So if this sounds a bit confusing, stage one, their velocity is very small, if not zero, but the acceleration is the full whack of 9.81. After a while, their weight is still the same, but there's a drag force against them, so the resultant force is smaller, and so the resultant acceleration is smaller. So their acceleration is now a bit less than g, and then after even more time, the drag equals their weight, and in fact, there is no acceleration. Acceleration is zero. They've reached terminal velocity, and that is the story so far. But then suddenly they release their parachute, and so at the top, I'm sort of talking. This is the picture in terms of acceleration up here. If over on the right side here, I talk about force. Before parachute, forces are balanced. Way, we've got the weight, we've got the drag. After the parachute, the weight stays the same, but the drag actually temporarily becomes huge. And so the resultant force is suddenly up. It's going upwards, and therefore you're actually accelerating upwards. And if you're suddenly accelerating upwards, like in an elevator, if it was really fast going upwards, you'd feel a sort of your centrifugal force, your inertia would mean that you'd feel slightly squished. And if anyone's been parachuting, when you deploy your parachute, you suddenly feel you kind of slam into your harness. And that is this sudden burst of acceleration upwards. Now remember, just because you are now accelerating upwards, that just means your velocity is changing to orient itself more upwards. That doesn't mean you're not still falling. It just means if you were going down, if you're falling to the earth at 100 meters per second, if you're accelerating upwards, it just means after the next second, you'll be still going down, but you'll be going down at 90 meters per second, and then 80 meters per second, and 70 meters per second. You're still going down, you're just going down slower. Okay. The cross-sectional area has increased. Yep, big parachute, and therefore the drag force also increases. The parachutist decelerates, or I've phrased it as accelerates, sort of against his motion. Same thing. The parachutist decelerates until they reach a new, slower terminal velocity. Yes, after a while. Yes, the cross-sectional area has increased, so D temporarily leaps up massively. You can consider these diagrams as a sort of story in themselves. But after a while, because you're decelerating, you'll be getting slower. And so that element of the drag depends on your cross-sectional area, but it also depends on your velocity. If you start to decelerate, then this drag force will also start to come down until once again they are balanced. The difference is they will now be balanced at a different terminal velocity. Okay? Where they're quite right to say that that terminal velocity, the new one, is lower than the old one. Okay?